I have copies now.
Who needs the copy?
Okay, you watching?
Do. Yes.
All right, now, as I showed you a minute ago, and as a little video clip showed you last period, when atoms decay, when they break up, when they are radioactive, a lot of times energy is given off. Okay, and we might wonder, why would they do this? I mean, what particular atoms are going to be radioactive, and how do you make them do it if they're not? All right, and well, it turns out there are a lot of different versions of different atoms, a lot of different isotopes, a lot of different nuclides. And some of them, the combinations of protons and neutrons, are more stable than others. Others are very unstable. Okay? Certain combinations of protons and neutrons just are not stable, not happy. Kind of like, remember how when we talked about for electrons, how, very stable, group 8. They want to have a full octet, the octet rule. That was a big deal for them. So guys like fluorine and chlorine and oxygen, they're right up there. They're real close to having an octet. They're going to be very reactive nonmetals, very reactive metals. Guys in group 1, if they just lose one electron, they drop down to having an octet. So for all of those reasons, you had unstable versus stable for electrons. Well, the same thing's true for protons and neutrons. All right, turns out that there's a band of stability. You don't have to write that down. That band of stability is on this chart I just gave to you last period. All right? And it looks like this. Band of brother stability. That's right. All right. If you look, this is a chart of the nuclides that are stable. I'm going to show you a different chart in a little bit. All right? This chart shows you, and you can see like a stepwise pattern in this chart too, which is indicative of the fact that there's probably energy levels even within the nucleus. Now, guys that are in this band, they're okay. They're happy. They're stable. They're not going to fall apart. Right? Remember the video? The guys, the radium's dancing around, then he becomes some other element, then he becomes some other element. That happens for guys who are out here or out here. But if they're in the band of stability, they're going to sleep. You got their nightcap on, and they're falling asleep because they're all happy. They're not going to change anymore. All right. Turns out that the most stable combination you could have would be even numbers of protons and neutrons. 157 of those nuclides in the band of stability are even numbers of protons and neutrons. And if I didn't make this clear, and if you didn't look, this is the axis that talks about neutrons. It gives you how many neutrons there are. And this is the axis for protons. And basically, somewhere around a 1:1 to a 1.5 to 1 ratio of neutrons and protons is the most stable, somewhere in this area. And I'm going to ask you this somewhere along the line on the test. Say I got a guy who's got 80 neutrons and only 20 protons. He's up here. Is he in the band of stability? No. Now, what I will really be asking you at that point is, what would he want to do to get down to this band of stability? What kind of radiation would he give off? Because there's lots of different kinds. We're going to talk about each of those, okay, in a minute. The least stable, by the way, would be odd numbers of both. There are only 5 in the band of stability that have both odd numbers of neutrons, like 3, 7, 5, and odd numbers of protons as well. All right? Now, I need you to be able to predict and complete nuclear equations for guys who are outside of this band of stability trying to get back home, trying to get where they will be stable. Okay, you guys, it's kind of similar to the way if I asked you, what does oxygen want to do when he forms a compound? What would you tell me? What does oxygen want to do when he forms a compound? Gain 2 electrons. Fluorine wants to gain 1 electron. Sodium wants to lose. You know who wants to lose and who wants to gain based on where they are in the periodic table. You know what kind of radiation these guys are going to give off based on where they're located. That's what I'm going to go over in a little bit. But first, I got to give you the names of all the different kinds of radiation they can give off. All right, not all the different kinds, but a lot of them. I'm going to make a chart of the different types of radiation, and you're going to make it too in your notes. This chart is going to have 3 columns to it. Okay, the biggest column being the last one. The first column is going to be the type of radiation, just what it's called. The second column will be the symbol for it, and the third one will be the description of it. Okay. All right, let's start off with the types of radiation. I'm just going to list them right down the line here, okay? You've probably heard of some of these. In the little video clip, they mentioned some, and maybe you've heard of other ones. Can you mention it? Anybody know any off the top of their heads what kind of radiation there is?
Ultraviolet.
No. Gamma rays, yep, that's one. And they mentioned another one in the movie. They said alpha particles. You ever alpha? What do you think? So if alpha's one, what do you think another one is? And gamma's one.
Omega.
Beta, yeah. So those are some of the alpha particles, beta particles, positrons, gamma rays, neutrons, and protons are all different kinds of radiation that can be given off by atoms that are unstable. Now, you don't know what any of those mean yet, but you're going to. You're going to have to because you can't complete the equations or predict what's going to happen unless you do know what they are. So that's why I have to do this first. By the end of this period, you will be able to complete the equations and even predict, at least the ones above the band. You're going to see the ones below the bands tomorrow and other guys tomorrow as well. So those are the kind I want to talk about. Is that all there is? Not necessarily, but that's all I want to talk about. Those are the major ones. These are the symbols for each of them. It's a case where, in the old days, days before, even my days, everybody would know what an alpha, beta, and gamma look like, the symbols for these guys, because you would have had to take Latin and Greek, and you would have had to take these other languages, to graduate from college or whatever. Now you would be surprised probably to see that guy looks kind of like a fish. That's an alpha particle looks like. All right, a beta particle it looks like a B. It has a little -1 next to it. Okay, or it's also another name and a symbol for a beta particle is an electron. A positron will be a +1 next to that B, or a +1 next to that electron. I'll explain these as I go over the description in a minute. A gamma ray kind of looks like a Y. Actually, it's not a very good picture, but it kind of looks like this. Like that. Okay. And a neutron and a proton are exactly what you'd expect them to be. They're a neutron and a proton. And you know what they are. If you look at these numbers that are next to here, here, and here, they are all set up the same way I showed you it 2 periods ago. If I were writing carbon and I had 14/6, what's that number there? The atomic number, or the number of protons, right? What's that number there? The mass number, or the number of what? Protons plus neutrons added together. Okay, well that's what these numbers represent here as well. And you're going to see it's important we know what they are and we write them in there because we're going to have to use them to balance the equations. And these equations are balanced a little differently than your old equations were. All right, finally, the description of each, what they are. Alpha particles are pretty large particles compared to these other guys. All right, alpha particles are basically helium nuclei. They contain 2 protons and 2 neutrons, mass number of 4, atomic number of 2. Basically a helium nucleus, not a helium atom, not the electrons that go along with it, but just a helium nucleus. And these are given off by a lot of large radioactive elements. Uranium, for example, you all know about uranium. We're going to talk about uranium. We're going to talk about the transmutation of uranium into lead and how it's, enriched to form nuclear fuel or a bomb. Okay, we're going to talk a little bit about each of those things. But uranium left to himself will give off numerous alpha particles on its way to becoming lead. Okay, and it will take a while for it to do that, by the way. Okay, we'll talk about that too. Beta particles are just electrons. But the crazy part about this is, you're not going to believe it, they're electrons that were ejected from the nucleus, not from the outer energy levels. But you say, well, I didn't think there were any electrons in the nucleus. Well, in the first example of a radiation I'm going to show you where they come from in a little bit. These are called positrons. They're basically like a positively charged electron. And that's tomorrow. We'll talk about those a little bit more. Gamma rays are often given off kind of like, all right, remember when we did quantum theory, and we excited electrons in flame tests. They gave off different colors. We excited the electrons went to higher energy levels. They fell back down. They gave off energy that we saw as light. Well, when nuclei change energy levels, when they drop down to a lower energy level, they often give off gamma rays, which are just a form of energy. They are at the very high spectrum, very high frequency, small wavelength energy that has a lot of energy in it. Gamma rays are up there, the sun, if you look at that chart or that poster over there. Nasty stuff, even more energy than X-rays, okay? Neutrons are just neutrons, and protons are just protons. All right, there's no real surprise for those. You should know what they are. Now, again, this is just a listing of them. As we do each of the types of radiation, I'm only going to do 2 types today. As we do each of these types, you're going to see how I'm going to talk about what each one of them is doing, why it's doing what it's doing, all right, and how you actually balance the equations for it. But for now, that's the chart. Those are the guys we're going to be dealing with. Okay. Do not write that down. That's where? On that same sheet. Okay. All right. Now, if you look at this, again, don't have to copy this down, obviously. This is the same basic band of stability we saw before, only it has guys outside of the band and what kind of radiation they would undergo. Now, how are you supposed to know which one of these they're going to undergo? Well, it may seem like it's impossible to figure this out, but it really isn't. And I'll show you as I do these how you'll be able to predict guys who are above the band, what they're going to do, and guys who are below the band. Now, let's just look at it. Guys above the band have too many neutrons. This is a graph of neutrons, right? These are neutrons. Okay, I really didn't need that. Okay, too far. That's what line. This is a graph of neutrons on this side and protons on that side. So if I've got a guy up here, he's got too many neutrons and not enough protons. What might he want to do to get himself down into that band of stability? Well, there's really 2 things he's going to do. I'm going to show you two major things he's going to do. He could give off neutrons. That's nice. That'll bring him closer down. All right. Or he could actually even convert neutrons into protons. Those are the 2 things he's going to do. All right, and you'll see that for guys above the band. Everybody outside of that band undergoes some type of radioactivity by emitting one or more of the kinds I just showed you there. Now, we're going to talk about the guys above the band first. But the ones below the band, they'll undergo different kinds of radioactivity. And there's other guys who are just so big, they're unstable and will undergo different kinds of radioactivity. Okay, so of all the ones I have listed above, neutrons, gamma radiation, alpha particles, beta particles, positrons, okay, all those guys, you're going to have to eventually know what type of radiation will be given off at what times. Okay, it depends on where they are relative to the band of stability. And a band of stability is, remember, just the ratio of neutrons to protons. How many neutrons it has to protons? If it's around 1 to 1 or 1.5 to 1, it's okay. If it's above that or well below that, it will do other things. Okay, we ready? Now, all I'm going to do are the ones above the band today. Mr. Wasser's above the band when he's conducting. He's standing up above the band. Sometimes. When you're playing and you're in the seats at the football game, and he's actually below the band. So depending on whether Mr. Wasser is above or below the band, he would give off different kinds of radiation. You didn't know Mr. Wasser was radioactive. Guys who are above the band, of course, they have too many neutrons and not enough protons. So here's what they will do. They will either undergo beta or neutron emission. And that is so they will decrease the neutron to proton ratio. They will decrease that ratio. Okay, we're finally there to where we could write something, do some equations. Let me show you what thorium does. Okay? And this is what you will get on the test. I might get for beta emission. Oh, by the way, I guess I have to define it too. Talk about it first. Beta emission, remember, this is the more confusing one. I'm starting off with this one. I guess I should take my time here. I know I've been rushing a little bit, but we did lose all that time for two reasons. Mrs. Rothman came in and talked to you guys, and then I also had to run and get an extra copy. We're short. So we're running a little short on time. I'm going a little fast, but I need to slow down for this one because this is the weird one. This is the guy that doesn't make much sense. Beta emission says that somehow or other shooting an electron out of your nucleus makes you happier. Makes you better. Why? Well, first of all, where the heck did that electron come from? And secondly, why would that affect the neutron to proton ratio? Here's why. Take a look. You're not just giving off an electron out of nowhere for no apparent reason. You just grabbed from an electron cloud. That electron came from something. See if you can figure out from where based on this little explanation. A neutron is converted into a proton and then releases, while it does that, an electron from the nucleus. Copy all that down and I'll explain. While you're copying it, I'm going to write this down over here. Don't write these down, what I'm writing down here. Okay, you got that copied? Don't write this down. Do not copy what I just wrote here. I'm writing that for a reason. You're just copying the definition down there. Can you figure out what actually makes up a neutron based on that? What do you think? Exactly. Look at, notice the neutron weighs just a little bit more than the proton, right? Where do you think that extra mass comes from? Well, partly from the extra electron it contains in its nucleus. It contains in that, it's in the nucleus there. All right, the two of these guys together, and they balance themselves out. Why is a neutron neutral? It's got a positive charge from the proton, a negative charge from the electron. All right, so when he gives this guy off, he becomes the proton. Okay, and when the neutron gives off that extra electron, because these two guys together. All right, it becomes a proton. So that's what's really happening here. A neutron is being converted into a proton. Now, whether or not you understand that, and I hope you do, can you complete the equation? Yeah, because that actually turns out to be really easy. Say I gave you, for my first example, thorium, and he was going to break up by this beta emission. He was going to give off a beta particle. What would you draw on the opposite side? Well, you would draw two things. You're giving off a beta particle. The beta particle is an electron with a -1 here. Okay? Now, the reason that -1 comes into play so much And all I have to do, remember I told you, it's very similar. You have to balance these kind of equations the way you kind of like you had to balance the chemical equations, but it is different. In chemical equations, could you get a new compound, a new element on the other side? No, you had to have exactly the same number of elements and kind of elements on both sides. But here, you will get a new element. What's that new element going to be? Because on that side, the denominators have to add up. The atomic numbers have to add up to the same number. It's 90 on this side. What must it be on this side? On the bottom. Anyone? I have a -1 there. 91. Oops. Oh, that's not good. A 91. I'm doing it by the simple way first, and then I'll show you why it makes sense in a minute. 91 minus 1 is 90, correct? How about the top ones? There's no number up here. It's 0. So what do you think this guy is over here? What does he have to be here? 234. What element is that? Well, don't look up there. You're not going to find him. He's only going to look at your periodic tables out because there's going to be on these. I told you, a lot of these are going to be way down low. What element is number 91? Get your papers out. I'll give you a hint. It's Pennsylvania. No. Look, get your paper out. I'll wait till Emily gets her paper out before we go any further. Come on. Everybody find it? What's his name? Protactinium, PA. That's why I said Pennsylvania, PA. All right, protactinium. Okay?
Actually, it says PR.
It doesn't say PR.
No, it doesn't. No, it doesn't.
All right.
Wrong line. Wrong line.
Okay, it's got to be a guy who's 91. Can you do this one on your own? Carbon 14. Carbon 14 giving off beta emission. What do you think is going to happen in that case?
It's going to be -180, and then it's going to be
Plus what? Well, and by the way, I want you to draw the beta particle this time. Draw it this way, because I can write it either way. You could draw it as a script B with a -1 or an electron. Either one of those, get used to seeing them in the book, in my worksheets, in my notes, in my homework, and in the test. You can write that as a beta particle or that as a beta particle. They're both beta particles.
it's going to be 8 on the bottom.
It'll be an 8? No.
Oh, 7. There's 7.
7. And 14 is what? Nitrogen. Now, so notice what happened here, guys, in both cases. Now that you've done it, you realize something about this. I hope you're realizing something here. These actually turn out to be really easy because all you have to do is watch and balance out, much easier than balancing out a lot of times with the equations we saw in the past. And the ones we're going to see in redox reaction will be much worse. It's just going to be a matter of balancing out the atomic numbers and the mass numbers. But just so we all understand what's going on here, the things that make this guy different. I actually have a brand new element. Here's carbon on this side. Here's nitrogen on that side. That would never be okay in Chem 1, in the early chapters of Chem 1, all right, in all the chemical equations. This is a nuclear equation. This is a nuclear change, all right? And secondly, can you see what actually happened here? If it went from 6 to 7, what happened to my number of protons? What did it do? It went up by 1. And if this number stayed the same, what happened to my number of neutrons? No, I lost 1. You see what I'm saying? And that's exactly what happens when a neutron is converted into a proton. You see it? All right, that's why it works. But in effect, it doesn't really matter because if you could do the math, simple math like that, you can do these. All right, next way you could do these.
Do we have to know an anti?
The anti-neutrino, no, is also given off as massless. It's not included in the equation. All right, take a look at neutron emission. This is the last one. We're almost out of time here. Now, this is the one, I say this one for second, and the last one we're doing today is the easier one. It makes complete sense that a guy that's got he's above the band, he's got too many neutrons versus protons, it makes sense that he would simply give off Jimmy Neutron. Did you see that? Karen wasn't watching. Here, I'll show it one more time. You gotta pay attention. There he is, Jimmy Neutron. Okay. It makes complete sense that he would do that. A neutron is simply ejected from the nucleus, and now he's got fewer neutrons versus proton ratio. Okay? And I was going to do a couple of examples of this guy. For example, 1. I'll take iodine, 137. If he's going to give off a neutron, can you complete that equation? I would hope so. Go ahead, complete that for me. He's neutron emission. He's given off a neutron. So what do you think? Is everybody okay with this? I'm going to have two things given off. I'm going to have a neutron. And the reason I told you a minute ago, you want to keep these numbers. That little 1, and you can put the 0 in if you want to. You don't have to. This has to still be a 53. And this one has to be what? 136. I knew someone was going to say 138. It's not 137 plus 1. It's 136 plus 1 is 137. All right, on this side, I've got 136 and 1 is 137. Now, what element is this? Well, it stated iodine. So, well, that's not a nuclear change. It's still iodine. Is it still the same isotope of iodine? No. Okay. All right, and finally, I wanted to do one more where I will show you, and the test and in the homework tonight. It's often, I always have a box here. It could be here, it could be here, it could be here. And you just fill in the blank. People will say, well, I don't know what ones that's called. It doesn't matter. You can fill in the blank. This happens to be under neutron emission, so it's going to be neutron emission. But it really doesn't make any difference. Can you figure out, just using the numbers, can you figure out what has to go where on the other side? Sure. What's going to be over on this other side?
17, 7, and...
Exactly. And if I asked you how many protons, neutrons, or electrons are in these guys, you'd be able to tell me that, I'm sure. All right, your homework is, it's up there on the board, page 548, numbers 6 to 10, and page 556, numbers 15 to 16.